Okay. All right, everybody. So let us begin. So first, I want to start with a preface. Okay. So the idea what we'll be doing on this whole series of lectures is basically I will try to like take standard quantum mechanics, the one you learn from textbooks, and to criticize it a bit. Okay, find weak spots and like basically to produce some arguments that maybe it can be rebuilt in a better way. And the bulk of this whole series will be actually us building quantum mechanics as a theory, starting from scratch, basically from basics. And this will be whole journey, right? So it will be excellent opportunity to talk about foundations of the theory if we are building those foundations, right, from scratch. So this is the plan. However, I realized that when someone comes in and starts talking about, okay, we will take some established theory, the one you learn from textbooks in a certain way, and starts to poking holes and replacing it with maybe some different formulation. I already hear, sharpening of pitchforks and lighting the torches and stuff like that. So the first lecture, maybe also the second one, I want to spend on like explaining myself. Okay, I want to convince you that in physics in general, the practice of like reformulating theories or refining theories, changing them, is not so uncommon. In fact, it's like this happens all the time. Okay, and usually it's maybe on smaller scale, that some small refinements here and there over the years, but sweeping reformulations also happened many times, although not in the case of quantum mechanics. Well, there were a couple of reformulations, but usually they spawned a new theory, like many-body theory or something like that, right? So we'll be doing something that maybe sounds like some kind of heresy, which burning on stake would be required here. But I want to convince you that this is not so heretical after all. This is kind of standard practice, maybe not standard, but
how all sectors start.
yeah.
Something heretics, but you convince ourselves that it's not.
Yeah. So and the other thing, my defense, okay, we also will be important because if we want to do something like reformulation of a theory or criticizing theory first, you have to have some framework to do the criticism, to do the analysis, right? Of what are the contents of the theory, how can you criticize it, what will happen when you criticize it, right? And what will happen if you start to, playing with it innards. So you need to have some kind of lens to look through, to analyze what is going on, right? So it's not to play blind. So this first lecture, which will be, on the one hand, it will be like establishing this lens of analysis and defense against pitchforks and torches. Okay, so so with this, I don't know how it sounded, scary introduction, but I just wanted to soften the blow because I will start talking about stuff that's not very standard. Okay, because we'll be talking about essentially theory of theories. Okay, we won't be talking about a specific theory, but physical theories as a concept. Okay, what are those physical theories? How they are constructed? And how can they be criticized? Okay, so it's kind of weird. It's kind of philosophical, although I wouldn't say it's philosophy because I'm not a philosopher, and it would be probably very real philosopher probably would be not very happy with what I will be doing here because it's amateurish at best. Okay, but I hope it will be interesting. At least this thing that I will be talking about today helped me a lot a couple of years ago when I started to like think about it, write some stuff about it, just to see how it tastes, and it helped me a lot. It later down the line, it really helped me focus, to understand what I am doing, why I'm doing stuff, what is fun, what is not very fun, what is sometimes even to have my own understanding what science is about, actually, what is maybe less scientific and stuff like that. So now I hyped it up very much, but so let me try to start it. Okay. So first let's talk about the structure of physical theories as a concept. Not some specific theory, but theories as a whole. So let's give it a title. Structure of physical theory. Okay, so I think that some people, maybe actually quite a lot of people, think that physical theory is very similar to mathematical theories. Okay, you can see it in some of the textbooks, in the sense that it's like mathematical theory, because you can just, the content of the theory is just some logical inference from some minimal set of axioms. Okay, so mathematical theories are theories that can be axiomatized. Okay, and then you just derive everything from those axioms. And some people think that physical theories work in exactly the same way. Just give some set of axioms, and then everything else is just a logical inference, just some theorems based on those axioms treated as truths. And I think this is a mistake, okay, that this is not really how physical theories work, because what actually, I believe that in reality, physical theories have two main components. One of those components, let's call it formalism. Okay, so this element, this is the mathematical theory part. Okay, so you have mathematical, all the mathematical bits are under the umbrella of formalism. Okay, but this stuff is completely abstract, right? This is just, you have some elements there that make sense within the confines of this logical structure, but they have no connections to anything outside, right? So to make those connections, to make those links to something else than its internal structure, is the second bit. Let's call it interpretation. Okay, so the role of interpretation is to be basically an interface between abstract stuff and how these elements of this formalism translate into things that could be experienced by the users of the theory. Okay, and by user of the theory, I mean any being, intelligent, conscious being that just uses the theory for some purpose. And of course, mostly we'll be talking about human users, right? But don't discount the possibility that there might be non-human users of theory. And this is kind of, it's an observation that's kind of important, because this already illustrates that interpretation is not, you can have the same formalism, you have theory with some formalism, and if the theory is to be used by humans, it will have certain kind of interpretation, right? For translating abstract stuff for human understandable things is certain kind of rules, right? Certain set of rules. But if you imagine that there is some, I don't know, space alien who is quantum in nature, not classical in nature, then they could use the same formalism, but then the rules of interpretation would be different for them. Yeah.
I don't agree with what you said. I think that physical theory is built on experiment. This is foundation. And then if you have experiment, you want to understand it. And then you invent some formalism, and then you interpret this formalism in order to understand the experiment.
We will
But
get to that.
What is missing here? But
No, we will get to that.
what you said, what is physical theory, it is like, that you can invent it being in a jail and not seeing the word, and then you invent some formalism, you interpret it, and then it is mathematics. Physics is experimental science, so you cannot talk about physics when you don't start with experiment.
We will get to that.
But you have to start with it.
No, I disagree. I disagree with that. I disagree with that. You don't have to start.
Because if I have only this, I can invent any physical theory.
Yes.
Any.
Yes.
But this is only one physics. Mathematics but maybe many, but not physics.
Yes. So you see, I'm talking about, I'm not talking here about what is the purpose of physical theory. I'm talking about what is made out of, okay? At this step, we will get to this connection of experiments, obviously. And it's kind of integral to this whole business. After all, the role of interpretation is to, translate some abstract, formal, mathematical statements into something that the user, human, can experience. So you can, of course, ask if, those experiences match up with what is actually seen in reality, right? So this will be a part of this whole story.
Without mentioning experiment, interpretation has no any sense in this. What you want
No.
You have formalism, you develop like in mathematics. You don't have to interpret the differential equations, partial differential. Interpretation is only when you want to transform the formalism into something that you observe.
That's what I said.
But that's what is here. It is just
It's like a
vacuum. You put it
That's
interpretation of what? Of what?
That's what I said.
Of what? Of
What?
what?
Yes.
With respect
Look,
to what?
okay, so let me say it again. Because you are going one step further, let's say. So the formalism is abstract maths, okay? Some objects, they mean nothing.
So don't write interpretation. Formalism, we want to create some theory.
This is the good name. You could call it some different way.
Experiment, there is no interpretation.
Disagree with that, and I will make my case. Okay, will make my case. Interpretation is a set of rules, right? How those abstract elements, some of them at least, from this formalism, should correlate with things the user of the theory can experience. This experience might be, what you observe in experiment, or maybe something else. Let's not narrow down too fast what we are talking about, okay?
As I understand it, is so that here you build a theory, let's say the core is this formalism, and then this envelope is the interpretation, and the natural, let's say, vector here is from the formalism via interpretation to the world, say, that is outside. But with experiment, it's slightly different that data from experiment is your input, yeah? So it's a little bit an inverse tree, but I understand that when you discover physics, you start from
we will analyze this in detail, okay? This connection, we will get there. We will get there. But the objection from Mariusz is that this is like the experimental data should be one of those elements that build theory. I disagree with that, okay? I disagree with that. It is important.
In mathematics, I agree with you, because mathematics is pure mathematics is invented by a human brain, and maybe you don't.
Mathematics is different.
About physics, don't write physical theory, structure of some mathematical theory.
No.
Then it will be okay.
I said, look.
Physics.
I said it in the beginning.
Experiment.
No. Not only experiment. Not only experiment. You see, I started from that. Formalism is the math. This is mathematical theory is only formalism. Okay, it's only formalism. Euclidean geometry is purely abstract. Okay, if you want to connect it to the world, you need another element, the interpretation. So let's talk about examples here. Okay, because you can say stuff like that.
You need real world first, then you need interpretation. If there is no real world, there is no interpretation.
Well,
What
You
would
said
be
in order to
No, no, no,
connect
no.
it to a real
No,
world,
no, 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 no,
you
no,
need
no, 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 no,
interpretation.
no.
So you assume that
No, 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 no.
Real
Wait, wait,
world
wait, wait,
exists.
wait, wait, wait. We will get there. We will get there. Okay, this is. I okay. Let's do spoilers. Let's jump forward. Okay, in principle, you could consider theories that are just bad theories. Okay. So you have some formalism, you define those rules of interpretation, and they predict something, and then you can you take this object in your hands and you want to criticize it in some way. Okay. For example, does this thing match with my experimental observations? Because I want my physical theories to match up with physical observations. And then you verify it, right? And you have the ability to filter whether this theory, you want to use it for description of real world, or maybe because it doesn't match with experimental observation, maybe you want to throw it away, or maybe you want to use it for something else, who knows, okay? The portion, the element of critique is very important to this, but it's not a part of the structure of the theory. It's something you add after all.
But you
Afterwards.
assume that it exists. I am talking from the perspective of somebody who is locked in a cubic room, totally dark, okay, has no any access to the real world, and when I think about formalism, and then you say interpretation. What I can interpret? I have nothing. I have no any single device to measure anything.
No, okay, no.
You assume that you can interpret your theory. It means that you can compare it to
Łukasz,
something
one
which
second, Łukasz.
exists.
I have a comment to that.
Does exist, except though that
Okay, so let me
look
give.
from my perspective. I am locked forever in a dark room, and I can create a formalism. I am smart. I can write equations.
Mariusz, if you allow me to continue,
Okay,
I hopefully will get to all the points you are raising. Look, I might be. This might be weird. Yeah, there is plan here.
Which is contradictory to what you say, because there's not something missing in this ordering, and you are referring, I will interpret, I will verify my theory by interpretation it to what? I am just looking at the empty box, and there is nothing else. I want you to mention that there is something else, except that there is world.
I will, but if you stop me at the first paragraph, it's just difficult. It's just hazardous working conditions. It's like, look, this might be weird. That's why I preface it with weirdness. Łukasz, 1 second. But there is some plan here. There is a method to this madness. Okay, if you just put some. Okay, I might be weird, but I'm not completely insane. Okay, at least I think so. There will be something that it will, this will be something useful in the end. Okay, so brace yourself. Try to enjoy the ride. Okay. Okay, Łukasz. Łukasz had a question.
Can you hear me?
I can hear you. Can you guys hear? I think I can make it.
Louder.
I think I can make it, go through the. I remember yesterday there was some. Oh, no.
Okay, takes time. If it takes time, then just forget about this. I wanted to mention string theory as a theoretical endeavor which has no direct connection to experiment. But, its connection to the rest of the physics, that it's promising, I'm not on loudspeaker, am I?
Well, kinda. People say they can hear you.
Okay, so yeah. Lots of our colleagues, okay, who call themselves theoretical physicists are working on string theory, which has failed to deliver any testable prediction, okay? The motivation for the effort, which lasts for like 40 years, is to basically provide, a consistent formalism and I guess interpretation, okay? connecting this, plugging this into general relativity and quantum mechanics and making them consistent. Without new experimental input, which is actually a big problem, okay? But as critical as I am towards, such an endeavor when it lasts for 40 years, okay, I would say it's still within the, it's.
Yeah. So
it shows that you can do theory motivated by things that are not directly coming from the experiment, but rather built on other theories connected to experiment. For example, trying to make them consistent. Okay.
Yes. So exactly, if we don't, this kind of split, okay, it makes possible for us to consider string theory. If we did it more rashly, like Mariusz is suggesting, that you first of all start with some experiments, however you want to do it, you would just discriminate against this kind of effort. And
sorry? I didn't say that there is a need for experiment. I say that first the real world must exist, then I can use to physical. The string theory is not physical, it is a theory.
Yeah.
So I am just complaining
the
about
physical theory.
The word that's physical. Without real world, there is no.
Okay. Let's.
Doesn't exist.
This is good. This is good. This is good. The discussions are good. I'm much less stressed now, to be real.
Because but now I stop.
Yeah, but this is
what I didn't say.
Yeah, but this is good. I like it. I'm thankful for that. Okay, I'm less stressed now in reality.
I stop.
Yeah, but let's. So because I hear you, Mariusz. I hear your concerns, and maybe there will be now I'll be able to a little bit smooth them out. Okay, let's talk about example. Okay, because I am a maturish philosopher, let's say, but what I learned, or I think I learned, is that when you do this kind of things, you have to you prove or test this idea with examples. Okay, so this will be I will do it like this. I will say something kind of general, and then we go to examples. Mariusz interrupted me before I went to example.
So, I have an even better example.
You haven't heard mine example. So
what was yours? I had to leave. I was not listening for a minute. I was thinking.
Yeah. So hold on. Let me say what kind of example. It's good. It's good. So let me consult my notes if I'm not missing anything. Yeah. Okay. So let's as an example of let's take just standard classical mechanics as an example of physical theory. Okay, the formalism of Newtonian mechanics is it's kind of simple, right? You have you would write some vector, right? That is a function of parameter t. Right? We have components, some x of t, some y of t, some z of t. Okay, so this is like a basic element from the formalism of classical mechanics. But if you are talking about formalism alone, this is real parameter t. It means nothing. This vector means nothing as well. So it's an element of vector spaces. It's well defined, logically consistent, but there is no link with outside world in any way. The link is established through interpretation, and even classical mechanics requires this kind of element, right? Because this is the interpretation comes in that this is time, okay, and this is position, okay. This is, but this interpretation is very simple in this case, because if the interpretation of time in this case, so how t corresponds to experiences of humans, well, the only way to really explain to other human what time is, you basically appeal to their intuitive understanding of the concept, right? So the interpretation for classical mechanics is simple in the sense that each element of the formalism is interpreted by appeal to intuitive understanding of the user of the theory, of humans, right? So, it's and the reason why it's so is basically because historically the theory was formulated in a like top-down sequence. So it's like first was intuitive, was a way people understand motion, right? Some intuitive understanding of time, of position of objects and stuff like that. And then was formalism, so the maths was invented to reflect those intuitions, right?
So from where this intuition comes from? How user can gain
By
this
living,
intuition?
by living,
By real world.
by real
Also.
world. Yes, yes, exactly. So-
I was objecting.
So this is where
In order, last sentence, in order to say physical theory, it means that you assume that there is outside world.
you see.
If you are sitting in a
Mariusz,
jail and
yeah,
you
yeah.
don't know that it exists,
But
you never create
recall,
any physical.
recall how it was, how I introduced this stuff. The interpretation translates abstract maths to how it would correlate with experiences of user. So the user is the thing that lives outside. Mostly it will be human for us, okay? But you know, there might be options for some sentient quantum computer AI, whatever. Okay, who knows? Or maybe some celestial kraken that devours worlds. Who knows? But if there was nothing outside, there would be no need for interpretation, right? Because there won't be users of
That's what I would
theories.
say.
Yeah. So
What I would write.
So you see,
there,
yeah.
there exists.
But there is a
Well-
slight nuance here, because you don't, to do this, you don't need to invoke experiments.
No, but observation. For me, observation is
Well-
experiment. That I see that something is moving, that the apples are falling down.
Yeah,
I don't call it experiment.
you live-
if I don't want. So,
Yeah, but you know,
at the top is there is some
user
word, you
user
create
lives.
formalism and you interpret the world within this formalism. And then this is for me the physical theory. Without this, it is not physical theory.
Yeah. So yeah.
If I just may, I think the stress for Piotr was here more to focus the difference between mathematical thing and the physical theory, in the name that in order to have physical theory, you need to have this interpretation, and
Yeah.
mathematics is just as it is. You have x, and x is a natural or a real
Yeah.
number, and you do not put any interpretation
Yeah,
about it.
no,
But
no
with the
meaning. Yeah,
interpretation, you already have a physical theory, which could be, for example, totally wrong.
yeah.
So a completely wrong prediction has actually no
Could-
connection
could
to
be.
reality. But you
But
can
I say
assume
there is no interpretation if you don't have word that you observe. That's what is missing.
Or-
I repeat it for the 10th time.
Yeah.
Interpretation is meaningless if you don't have outside
If
world
you
that
don't
observe.
have a user who probably lives in outside world, in some world.
There's no mandate
Some
to do the
universe.
theory at all also, yeah.
But if you imagine some, I don't know, some kind of universe where users are just brains in a jar, who knows? Don't deny them physical theories. Don't be such.
If they are able to observe.
I mean,
Some-
who knows? I mean, I think therefore I am. Who knows? Let's not, let's not discard. Let's not be so radically anthropocentric. Okay. Let's leave wiggle room for some stuff. And the string theory is kind of a good example, because it's there is some, you might say all those people who are working on string theory are just stupid or just wasting resources or something. But there is some value in it. Okay, maybe not to predict, to give you concrete predictions of some experiments, but there is some value in it. There are use cases for theories other than just converting inputs into outputs, which can be compared with experimental results. This is something I want to say. Okay, there is more to physical theories than just being a black box that converts inputs into outputs that are kind of close to experimental observations. This is what I want to convey with this. And a couple of paragraphs later, there was nicely constructed sentences that would lead us there. Okay, but okay, we went ahead a bit. So okay, so where were we? All right, so like Hubert said, yes, I agree with your interpretation of my interpretation. Okay, this is what I want to say. I want to make a clear distinction between just mathematical theory, which is just a bunch of axioms and logical inference from axioms, and physical theories, because they require this interpretation. And this interpretation, if you think about it, it's supposed to translate to what humans can experience, how humans experience stuff, the time, position, whatever else. You cannot axiomatize this in the same way as abstract mathematical theory. So there is if you could, then there would be no difference between mathematical theories and physical theories. If you want to make interpretation, if you want to formulate it, it has to be a little bit fuzzy. Okay, there is some room for not being completely precise. If you would try to be completely precise, and I know, formulate your interpretation in some how do you call it? Legal lingo or something, unreadable stuff, you will still fail to completely form complete self-consistent system. Okay, because even law requires arbitration, right? So that's why physical theories are not math. Physics is not math. Okay, because there is this component, the interpretation, which is fuzzy. Okay, it's not axioms. Someone tries to axiomatize quantum mechanics, they are just wrong. Okay, that's what I'm trying to say here. And often people use the language of axioms when talking about quantum mechanics. Okay, sometimes even write textbooks where they start by listing some axioms.
But they don't give the full list of axioms. Some.
Yeah, exactly. Which already defeats.
Still room for some not precise.
Yeah, but already defeats the purpose. Well, why are you doing this if you don't complete it, right? But it's like maybe they just don't notice it. Okay. All right. So that would be so here the example of interpretation for classical mechanics. Like for this example, I want to say that it is simple in a sense that it's the rules of interpretation are just appeals to intuitive understanding, which Emilia asked, where do you get those intuitive understandings? Right from, like, you are human, this is where you get them, because you are human. Okay, so it's very simple, very simply constructed. So, okay, so that would be for classical theories. Okay, this may be, okay, let's skip this because we already used up a lot of time. So, okay, so let's go to the examples where interpretations are not so simple. That is let's pick some non-classical theory. A good example is Einstein's theory of relativity, okay? It is non-classical in the sense that there are elements in the formalism which cannot be interpreted by direct reference to some intuitive understanding of things. So let me show examples of what I mean. So non-classical theories. So example of theory of relativity. Okay, so let's see what's going on here. So so like a position vector of position depending on t on time in Newtonian mechanics was like the basic element of the formalism. So in special relativity, you have a 4 vector, right? Which has a 4 components, the time component and special components, right? And as long as you are talking about these events using this 4 vector to describe things that happens in your personal reference frame, then this is completely classical. Time, t is time, position is position. So this 4 vector tells you that the thing happened in position x, y, z from your point of view at time t, okay? Where things start to become difficult is when you try to compare points of view of observers who are moving with respect to each other with some constant velocity. In other words, the rules, formal rules for transformation between reference frames, inertial reference frames, are different than those of classical Newtonian mechanics, okay? And the difference lies in the way they treat time, for example, right? So in Newtonian mechanics, when you transform to any other reference frame, time is always the same, it's unchanged, right? So this leads to the interpretation that you have a universal simultaneity, however you say it. When an event happens at time t for one observer, it happens at the same time for every other observer, okay? In theory of relativity, the transformation to different reference frames mixes up time and space, okay? So let's say time in reference frame that moves with velocity c would be given by time in the original reference frame, how it goes, v x c square, I think, right? 1 minus v square c square, right? So time is different for different observers, to the point that even sequence of events the order of the sequence can change depending on where you go. So this immediately shows that you cannot interpret time in this case by appealing to intuitive understanding, okay? It will just fail. And if you don't believe me, because maybe it is intuitive, maybe I'm full of lies, let's say, you can consider a thought experiment. Okay, this might be useful. So if you imagine that we have that we are standing somewhere here, this is we, and there is a platform and wheels, and there is our friend standing here, and they are waving to us, okay, saying goodbye. And now the platform starts to go away from us with some velocity that's close to c, okay? So when you look what the theory of relativity tells you, it tells you that you will see that the faster the friend is going, you will see them slowing down. The waving gets slower and slower and slower. And it's not only hand waving, but also all the physiological processes inside them are slowing down. Everything slows down, okay? This is how you see it. So now imagine, let's do an intuitive transformation to their reference frame, okay? Intuitively what we would think about it. So if everything slows down from them, including how fast their brain work, so that like their effective frame rate is dropping, right? So for them, then we should be speeding up. Our motion should be like Jacob's Ladder movie, the and stuff like that. That's what our intuition would tell us, right? Because intuitively for us, simultaneity is universal, right? And of course, this is wrong, because according to the rules of the formalism, the transformation rules of relativity, this switching in reference frames is symmetric. So if we see our friends slowing down, they will see us equally slowing down. Okay. And why? Right? Because we intuitively we believe in we know nothing else than universal simultaneity. We cannot comprehend when it's not the case, right? So what then? If time cannot be understood, cannot be interpreted by appealing to intuition, because with thought experiment, we just showed that we would fail at that. So what can you do? And here comes Einstein with his big, wrinkly brain, and he had this excellent idea, or maybe he just adapted it from others, from Poincaré, for example, that okay, if we cannot directly deal with time, we cannot just directly reference some intuitive understanding, then let's do a trick. Let's identify the time with a readout of some measuring device. Okay, the device itself should be intuitively understandable for humans. Okay, in this case it will be clocks. So Einstein said, imagine clock. You know how clocks work. You deal with clocks all the time. So we won't be delving into the inner workings of the clocks. Just we rely on our intuitive understanding how clocks work. Okay, and now when you are talking about time in your reference frame, you have your set of clocks distributed in space. Okay, and you just say the time event happens is when the clock at this point of the event records, right, the event, and then afterwards I can go to that clock, pick it up, look at it, and okay, this was the time when the event happened. All right, and our friend here would also have their set of clocks, and they would deal with them in the same way. Okay, but now if you want to compare what is their point of view and versus our point of view, we have to compare the clocks. Okay, and if it was classical mechanics, the clocks would always show the same thing, but in the theory of relativity, they show different things, right? Dilation of time and stuff like that. So, in other words, interpretation for non-classical theory can be built by, rather than directly going for intuitive understanding, you go indirectly. If there is an element, non-classical and intuitive element, you project it on, let's say, classically intuitive stuff by going through some measuring device. And the device itself hopefully can be treated as a primitive notion of the interpretation, the thing that's completely intuitive. Yes, Mariusz?
Question. Do you make it equal classical and intuitive? Is it the same concept in what you are saying now?
And if we are talking
non-intuitive, it means non-classical.
Very good question. So when I say classical, when I intermix in classical and intuitive, this is because we are talking about humans. Okay, for humans are classical. So the things that are intuitive for humans are classical things. So classical theories are those that are completely interpreted by appeal to intuition. Okay, whenever humans cannot intuitively imagine something, then it's non-classical immediately. But if we're talking about space aliens, celestial krakens, for them they would probably need devices to interpret Newtonian mechanics, but clocks wouldn't be necessary for them, right? So for celestial krakens, theory of relativity would be classical. Okay, a very good question. So yeah, devices. So for this whole idea of devices to work, right? It has to be like the device itself cannot be a mystery, right? So if you need to spend more time on explaining how device works and to interpreting the device itself, then you're just not progressing anywhere, right? So it's always very interesting point when the non-classical theory has to appeal to devices, right? And this is, and I would hazard a guess, or maybe, okay, I'm making an official statement. All non-classical theories will use devices, measuring devices in some capacity, okay? The more devices you have to use, the more non-classical theory is. So I guess, I don't know what kind of devices string theory would use, but I'm sure they would be very, very weird, and probably maybe they would fail this criteria of being, not having to be explained. Quantum mechanics, for example, is well, it's also non-classical theory. So in this respect, is kind of similar to theory of relativity, but it's more. It's just a matter of degrees. It's still the same principle, right? It uses devices, but quantum mechanics uses devices for everything, essentially. With theory of relativity, right? If you are staying in your own reference frame, you don't compare with others, everything works classically. You don't need clocks. So when you compare, right, you do transformations between reference frames, then devices comes in, and it's only one device, clocks, essentially. Quantum mechanics, there is no respite. I mean, you cannot hide. Everything is devices. Okay, so it's very much non-classical. It's like extremely non-classical, but the principle is the same as with theory of relativity. That's why I always stick to examples with theory of relativity, right? To a little bit demystify quantum mechanics in this sense. Okay, so devices are very important. Invention. Yeah, we did that. Yeah, okay, we can skip this. By the way, the stuff I'm talking about, I have this text here. It's probably more eloquent than I'm able to say it. So it's kind of not finished yet, but I will post it in a couple of days on the website. So if you think I'm just babbling.
But this will be non-classical. What we are talking is classical because we can feel it by our senses.
Yes.
When you support it with devices, it's not classical. Because you support it with...
Well, you know what? Okay, this is actually a good point. This is a good point because measuring device, classical theory also uses measuring devices, right? Because yeah, exactly.
But my senses are also measuring devices. I see that something is moving. I predict that this bicycle will be at the tree in 1 minute, and I...
Yes, so I skipped a part, but now it's a good opportunity to go back to this part, right? So we're talking about position in classical mechanics that just appeal to intuition. I mean, people know what it means that the thing is somewhere, right? The thing is here, the thing is there. This is what this vector is supposed to represent. But but there's still this this vector XYZ. It's in certain point of view. It's in certain reference frame, right? And there could be different reference frames. Those numbers would be shifted around depending on what kind of transformation you have to do between reference frames. So it's not that simple. Like, that you have to put some meat on this whole statement or just intuitive understand, and you can do it quite easily, still appealing to intuition all the way. Because if you want to to really interpret what this R vector means, you would have to do some constructing, imaginary constructing, but still, or maybe just real physical constructions. So if you imagine that you have three mutually perpendicular axes, measuring sticks, let's say with notches cut into them in equidistant intervals, right? And you just put it on your head and carry it around, right? Then whenever you see something is at some position, then you can just trace project it on your measuring sticks and obtain XYZ for this object, right? And the other way around, if someone gives you XYZ, you can just trace it back to some position in space, and oh yeah, it points to that. So, but it's still, you know, the fact that you have measuring sticks and you can trace it from object to the notch, this all, I don't have to explain it any further. I couldn't, even if I tried. I just have to appeal to your intuition, how you would go about it, right? And another point is you can also intuitively imagine what would happen if someone else looked at some object, right? You know that they will perceive it that at some different point than you are perceiving, right? So you can do in your head transformation to different reference frame, to different set of those measuring sticks, right? And this is still, all this stuff is, I have to appeal to your intuition. I wouldn't be able to like explain it to you what happens. If you, I know, even if person is blind, maybe sensory depraved completely, you would try to, but then how you communicate with them? I don't know. Let's not try doing that. But essentially, we are appealing to intuition all the way down, right? But in this case, for classical physics, this is kind of, you know, we are doing it because we can. I gave you a recipe for the measuring sticks, measuring devices, because for some pedantic reasons, right? But with non-classical theory, there's this conceptual reversal, right? While in classical stuff, the measurement was afterthought. You don't have to specify too much, at least in case of position. But in non-classical theory, the measurement is the measuring device. It's what gives us, yeah, the access, any access. So there is this is a big conceptual reversal, right? This is what, you know, classical theories are very much different than non-classical theories, okay? All bets are off. There's, you know, things that are afterthought in classical here are fundamental for starting anything even, okay? So thanks for the question. It gave me opportunity to go back to this point, which I like. It's maybe not super necessary, but I like it a lot. Okay, so the next point, having this, I hope you're not bored too much.
Yeah.
Okay, not yet. Good. That's, you know, my main point is to have fun here with you. So the next point, we have this established somewhat. We're getting to the experiment stuff. We're getting there.
I couldn't explain it, but
So the next point I will entitled it ever-changing theories. Remember, I'm also trying to get pitchforks out of your hands here, you know. So I'm explaining stuff, but also trying to save my skin here. Ever-changing theories. So point that it's maybe not super obvious, but you think about it, it's becomes quite evident that once you have your theory, you have your formalism, you have your interpretation, it's not typically set in stone, okay? It will change, it will evolve over time, okay? People will do some refining to your theory, to the theory, right? They will be tweaking the rules of interpretation. They will maybe do some modifications to the formalism, okay? For example, again, examples are important. If you go to classical, our favorite classical theory, so in like the bare bones formulation, let's say, it's imagine this is how Newton spawned it. It would be the formalism would be just that m times r second derivative is equal to some function f of r and t. Okay, and now if someone else comes and say, okay, if I add to my list of elements in formalism, I add f g, that's minus constant m r square. Okay, and I add the interpretation that this is the force exerted by massive bodies on each other, gravitational force. Well, this is a change, a refinement of theory. I added element to the theory. Okay, it's very trivial example, but this is what I mean by theories changing, being refined. Right? This is super trivial. If you add some more, expressions for forces, that will count as a refinement as well. Okay, but this is the most basic, the easiest thing to imagine. There are of course more interesting examples. Let's take Einstein here again, right? Because you can imagine that Einstein started by taking the Newton's classical mechanics and saying, okay, I want two things here. I demand two things. One, that laws of physics are the same in all inertial frames of reference. And so Galileo law, I think this is how we call it. And two, that the speed of light is constant everywhere. Okay, in all reference frames. Okay, so came in, you look at the transformation rules for changing reference frames in classical mechanics, and they won't satisfy Einstein's demands. Okay, you have to modify the rules. So you come in with Lorentz transformation, which satisfies all those demands, but then this creates a need for changes in interpretation because universal simultaneity doesn't work anymore. So you have this come in, you want something from a theory, you start changing it. This change, let's say in formalism, creates a need for change in interpretation, but also change in interpretation can create needs in change in formalism. And you have this interesting back and forth between those two elements, which kind of shows that they are equally important. Okay, if one can change the other, then none of them is special in this sense. Okay, so sometimes you might feel that the mathematical thing is more robust, axiomatized, so it's like more sacred in some way, and the interpretation is just bunch of words, right? It's fuzzy. You can just hand wave it away. But no, it's equally important as the mathematical bit. It would be a mistake to not give them enough the same kind of attention. Okay. And this is
some comments.
Yeah, sure.
To this example, not to what you said. This is not a good example of what you said.
Refinement.
Because without the second equation, the first equation is not a theory. It says n times r is something. This is not theory, unless you say what is something. This way I can create theory of everything. I will create something.
I mean,
this symbol
yes, I agree.
Deviations from the word from the laws of nature are zero. And that's why one equation I created theory of
so I guess Newton started with gravitational force, right? And then you add the oscillator, there's harmonic oscillator, that would be refinement. Yeah, okay, that's true. I was sloppy here. Okay, forgive me for my sloppiness. But, we have time till 12. Okay. Good. If anyone getting tired, we might make break or maybe, I don't know. Go on. Good.
It depends how long it will be.
I mean, not longer than 12. Okay.
If I don't interrupt.
If you don't, no. Even if you interrupt to your heart, we have time. This is we have time for discussions. This is better. I was worried that I would be just sitting here, sweating and just reading from the paper, but there are discussions which relax me a bit. This is better. Good. Thank you, Mariusz, for that. It's good. It's very good. Right, so let's go back to refinements of theory. Einstein came in and did a lot of stuff. Well, in the end, we understand that this actually, the changes were so sweeping in their scope, right? That it was prudent to say, okay, now we have a new theory, essentially, theory of relativity. But this is like, so classical theory Einstein came, demanded some stuff, changed interpretation a bit. This did all this cycle of changes. So classical theory evolved into theory of relativity, essentially. But what is interesting about this is like it didn't overwrite the classical theory, right? So it was more of the fork project into two branches, right? Even though theory of relativity contradicts theory of non-relativity of Newton. They are in contradiction, but they're still used to this day, right? With understanding that one is not the scope, but the domain of classical theory is a little bit narrower now, right? We understand this a bit, but still they can coexist. There are use cases for both, in other words, okay? There are use cases for both. So
this is because these are physical theories, not mathematics. Mathematical,
yes.
they contradict each other. But
yes.
if we are physicists, we know.
No. You know, Mariusz, no. Mathematically, they don't contradict each other because you can still have, you know, the theory of.
Okay, theory is theory, but when you add interpretation.
Yeah, then they in contradiction.
Then
but if you add interpretation, it's not mathematical.
At some range of parameters, they contradict, but not much, and you can use the other.
Yeah, so you see, you can change. There are reasons to change theories, and even if you do that, formalism, interpretation, both at the same time, even very much, you are still. I mean, it's not a replacement. It's you just create more. It's okay, and it was done before, right? As an example of theory of relativity. Fork, okay, KK. Back and front, KK. Let me realign myself. What is the next point? Yes. God, I just lost my place. 4-1. Here it is 5. Okay. Good. Now we're getting close to the first bit, the experimental stuff. Okay, so we are seeing here that there is theories are changing, right? But why? What is the reason to change your theories, right? What is the catalyst for that? What is the driving force of those changes, right? So I think maybe I'm getting crazy here, but I think we can also analyze this element of this whole story. I gave it a name, tried to be fancy. I call this element oh my God, too many papers. So driving force behind changes. And I called it critique. Not criticism, critique. I want to be fancy. Critique with your pinky upright. Okay? So it's a critique. This is how you spell it? E, right? I want to, okay, critique. Maybe accent also, critique. So this is, oui? Oui. Yeah, so this is, you can think of critique as an umbrella term that holds a bunch of questions and demands you can level at your theory. Okay, it might be some hardcore philosophical questions about ontological status of this element of formalism or other, or something more practical, right? Like, I would say that Einstein coming in and saying speed of light must be constant, this is maybe kind of a critique, right? Because he came in and demanded stuff, let's say. But the critique is like the element of the story, but it's not a part of the structure of the theory. It's something that you add to this whole thing. This is the thing that causes the change. So Okay, so let's look at some examples. Okay, so I would say that like the simplest, the most vulgar type of critique would be if you ask, is this theory self-consistent? I mean, you ask for logical consistency here, right? Is the formalism a well-formed, non-contradicting mathematical theory? Is it true that when I take some statement, formal statement, taken from the formalism and apply all the rules of interpretation, do I get some paradox? So it's just the bare bones, like you simply treat your theory as a formal system and you ask, is it non-contradictory? Okay, that would be like the simplest type of critique. I call it simplest, not because it's easy to formulate or easy to answer. It's probably one of the hardest things to answer, right? If everything is logically completely tight, probably it's not, because interpretation is kind of fuzzy. But it's simple in the sense that it is most formalistic. Okay, it's like for computers essentially. It's not very interesting. I mean, if you detect that you have some, contradiction on contradiction, paradox on paradox, it's probably something wrong with your theory, right? But that's doesn't happen that often. Okay, so and from the point of view of scientists, physicists, this is not like the first thing you think about when you want to critique your theory. The first thing you think about, and we had an example of that, is it consistent with experimental observation? This is literally, we saw that this is the first thing you ask, right? For physicists, this is the thing what you do. Because again,
Doesn't have to be like this. My critique could be based on whatever obsession I have, for example, that, oh, I want this equation to be linear and it's not linear.
yes,
Oh, I want this equation to be symmetric with respect to whatever, and it's not, but it's not necessarily a physical requirement in the sense that it is required by experiment because I have some results that do not necessarily. Look,
Einstein, for example, required, his obsession was that all physical laws look the same in initial frames of reference. It's not, some weird discrepancies in experiments didn't I'm blanking on the word, did not imply that this is the thing that was missing or something like that.
Can I make a comment?
Sure, Łukasz wants to.
So Einstein was motivated by the fact that from Maxwell's equations, you get speed of light always c, okay?
No, but that's about c.
Yes, okay. No, but the point is that in Maxwell's equations imply speed of light, which is the same no matter what reference frame you are, okay?
Yeah.
If you put on Newtonian or the Galilean relativity principle on top of Maxwell's equations, things are weird, okay? But the point is that although that's why people introduced ether. But the point an interesting point is, although in the end there was an experiment disproving the existence of ether and showing that the speed of light is the same in all the directions, the Michelson-Morley experiment. The point is that Einstein didn't know about this experiment. Okay, he was only motivated by maintaining generalizing the principle of relativity by making electromagnetism, Maxwell's theory, consistent with. He didn't know about the experiment.
So it's you can call it obsession. Sometimes it's just intuition, but it's genius intuition. You see something.
But know how many other intuitions or obsessions were simply wrong, and I don't know if it's being genius or being lucky.
Look, if you
just have some obsession, which agrees with the reality, so you are a genius.
You're producing many obsessions of this kind, just like because this is like what Einstein was. His obsession was that he looked at something and he imagined, okay, is this thing like a general principle? that would apply in every theory. That was his kind of obsessions, and you can see it everywhere in his the way he did physics, and he produced a lot of those obsessions, and some of them were misses probably, but many weren't misses. So luck, it's not like skill, man. It's not at this point it's skill. If you are consistently doing discoveries, which are by definition unpredictable, then there is something you're doing that is, there is something you're doing that's right. You have some skills. But you could be just obsessed and just, of course, if you come in and just obsess about something and do nothing about it, then you are just a cook, a crazy person. Because it's good to be constructive with your critique. Right? That's why this is a driving force for changes. Okay, but obsessions. We'll get back to obsessions, but first experiments. Okay, right. So another type of critique that's important for physicists, for Mariusz, very important, rightly so. I don't disagree. But you see, I'm bolting it on. It's not inside the structure of theories. There might be still disagreement between us, but I'm bolting it on. It's adjunct to the rest. But right, if the role of interpretation is to translate abstract stuff to something that user can experience, right? A natural question is, does this prediction match with what I actually experience, right? So hence, does my theory, predictions of my theory can be confirmed or at least not be contradicted by experimental observations, right? This is a very no-brainer critique. Sometimes people say that this is like the essence of the physical science. This is what you do. You will essentially address the problem of predicting experiments or phenomena, which are like kind of experiments in a way. But I will be a little bit maybe controversial here because I think this is kind of shallow critique. It's not very productive. It is important for sure, like checking for self-consistency is important, but it's like doesn't give you much.
It's shallow
About experiments, yes, it's shallow. Look, if you
hard to argue, but it's shallow.
no, I will make my case. Okay, you can argue. I'm ready for arguing. I came here to argue, for debate. But look, if your theory is extremely simple, like Stefan Boltzmann law, or Boyle's law, or Kepler law, or something like that, which is essentially a theory that boils down to that it is a best fit to some experimental data. Okay, so the only purpose of this theory, the only thing it does is like to interpolate between data points, right? It's just some function that you can interpolate between data points. The critique of does it match the experimental results? It's like essentially the only thing you can do here, right? So if you do your interpolation, but you detect that there's no contradiction, it fits. Okay, you do the measurement for the place that you predicted what would be, and it matches. Great, the theory is perfect. No need to change anything. But if you detect that there is a contradiction, well, then the theory is not fit for purpose. It's essentially negated the whole reason for its existence. And in that case, you can do two things. Either you just throw it away. Its cost is little, it's just one function, one fit, whatever. Or you just say, okay, right. So I would just redefine the purpose of this theory, that now it will be used for interpolating, but in the range of data where there were no contradictions. And you can do that. So in case of those simple theories, which are still theories, asking for experimental, coherence with experimental results is like, it's basically the only thing you can do. And I mean, the more holistic, more complex theories are kind of modern invention, really. So this idea that asking for 11:30, so we have still half an hour. The idea that it's like the theory, the point of theory, the use case for theory is to give you predictions of experiments. I think it's very much tied to this idea of olden theories, like theories that we had in like 18th, 19th century. You know, you had Faraday law, you have Ohm law, you have whatever the hell law for circuits, and you know, and all this other stuff. They were just fits to the Ampere law. Okay. Yeah. But once we, you know, the Maxwell came in and just unified, and all those specialized laws became just special cases for your more holistic theory, right? All of a sudden, this critique of experimental data became very, very boring, right? Because look, if you apply this critique, and you just tell to your you want from a theory to give you a prediction that you can test experimentally, and if you think about it, getting a contradiction with experiments is just slightly more interesting than not getting a contradiction. Okay, in this sense. So for example, if you get imagine that people measure very carefully the orbit of Mercury, okay, and they discover that Newtonian gravity is there's a discrepancy there, okay. What do you do with this information? It doesn't really tell you what is wrong. There's some indication that something might be wrong, but where, how, you don't know. So, and it also does not invalidate your theory. It just narrows, right? Okay, so Newtonian gravity, I will use it for when relativistic effects are not important, right? But if you imagine that this measurement of Mercury's orbit was done before theory of relativity came out, because it was, you know, it was done to confirm or to, you know, test theory of relativity. But you imagine that it hasn't been thought of yet. You just measure Mercury for some reason, and you try to explain the motion with Newtonian gravity, you see discrepancies, slight, but still discrepancies. There is no way to get from that to what you have to do to actually evolve your Newtonian mechanics to theory of relativity. It's just not enough information. Maybe if you did enough experiments and you were insightful enough to like connect all those distinct experimental results, essentially something that Einstein did, although Mercury wasn't on the cards, it's just some other stuff, that completely unrelated stuff. And he just, you know, all his concessions and demands came into place, right? So in other words, if you are doing complex holistic theories, which we are thinking about, quantum mechanics is an example, like just simply thinking as a you know, experiments, matching experimental results, it's like all you care about. That's not all you care about, really. If you did, you know, everything will be boring. There's very little incentive to do anything if you're just testing for experiments. If anything didn't match, you just discard the whole theory. That would be just complete mistake, right? You have contradictions with classical mechanics. You can find them all everywhere, but you still use classical mechanics for their purposes for it, right? So it's like, so there is more. In other words, there is more to this critique than just asking for experiments. There is something else. Okay, and this brings us to the main event. So the type of critique that I think is most powerful as a catalyst for change in theories is a critique leveled at explanations that theory provides. Okay, but let me explain what that means. Let me explain explanation. So again, theories have many uses. One of the examples, we just talk about predictions for experiments. So when you use in this mode, the predictive mode, let's say, predictive power of theory, so what you are doing, what is enough to do is essentially you take your formalism, you take your interpretation, and you pack it into a gray box, right? That takes inputs and spits out outputs. Outputs is the predictions, which you can compare. Inputs is some initial conditions for the experiment, right? I call it gray box because if you are interested in this predictive power, even though we kind of understand what is inside the box, the elements of formalism, elements of interpretation that are there, but if inputs and outputs is the only thing, the relation between inputs and outputs is the only thing that we are interested in, then it could be a black box and it wouldn't change anything for us, okay? So if you want to open the box, look what's happening there, then you are explaining. This is where you're using theory to give you explanation. Explanation for an experiment, or explanation for a phenomenon, okay? And how, so when you open the box, you want to create explanation, and to formulate explanation, you essentially asking how those elements inside the box interact with each other to take those inputs and change them into some outputs. You want to, trace what's going on. You want to model it, explain it, in other words, right? So opening the box is the explanation. If you close the box and just go input output, it's just predictions. Okay, so now, critiquing explanations is you critique what kind of explanation, how good they are, how interesting they are, how exhaustive they are, how sane they are when you are opening the boxes. Okay, you just.
So is it a critique of this explanation more of the mechanism you have? So about let's say those obsessive-like things that okay, this is maybe good in many cases. However, I would like to have this Galilean.
Yeah. This is all converges here. Okay, so the type of explanation, the form explanation can take depends, of course, on the theory, the formalism and interpretation, how they mesh together, right? So this is very case sensitive. You look, one theory gives you this kind of explanation, then some other, and it's incapable of giving some other type of explanations, right? So it's all dependent. So when you come in with your obsession like Einstein, so what he was actually doing, he was taking the explanatory power. He was testing explanatory power of classical mechanics. He was looking what kind of explanation classical mechanics gives us, and was like a hawk hunting for, those explanations involve constant speed of light? Does those explanations involve, Galilean principle that everything is, physics is the same, inertial reference frames? He found that the explanations don't agree with those obsessions. I said, okay, so the theory sucks. It has to be changed. I want explanations to involve those obsessions of mine, because they're obsessions, but in reality, he had great intuition that those are principles, like physical principles. They should be everywhere. And and this is the thing that's more attacking explanation, attacking open boxes is the critiquing, maybe not necessarily attacking. This is how you do science, in my opinion. This is what drives the progress in science. This is what drives how theories are changed. Okay. And to give you a great case study for all of this, is actually again, classical mechanics has all the great examples, because depending on how how you went through your education, but maybe you heard that classical mechanics, you have Newton's formulation, the 3 Newton laws of motion, right? And you have this equation that we had, the differential equation. It was somewhere here. Oh, here it is, right? But there are also other formulations of classical mechanics. Hamilton's formulation, Lagrange formulation, there are a bunch of them. There are many reformulations of the theory. It's still the same theory. The experimental predictions are always the same. They always agree on that. But the way they are structured, the formalisms are completely different. And formalism is different, interpretations are different, explanations are different. They cannot be the same. So, for example, with Newton formulation, you explain all motion with forces. If there's some forces, there are balanced or non-balanced, this is what causes the motion. In Hamilton's formulation, the same motion is explained without reference to forces or things like that. So some energies, some principle of least action, whatever the heck. It's kind of weird, but also very elegant. And to make things even funnier, and it's like, why Hamilton's formulation? What is the catalyst? What was the motivation for doing that? Well, the motivation was critique of explanations provided by Newton. The forces are problematic concept, okay? And always were. And people were trying, there are many formulations of classical mechanics because everyone tried to get rid of forces, essentially. They didn't want to have explanations in terms of forces. And they came up with many different formulations with many different explanations. And the same theory still uses different formalisms, different interpretations, and they coexist, okay? You can see, you use each one of them because they are useful in different ways. And they're like the only real problem is like, the explanations, the interpretations are kind of different, incompatible even, and you have to deal with it somehow. And there are many ways to do it. I think in case of classical mechanics, it's like, okay, forces are not, it's like the Hamilton explanations are fundamental, such as balancing of energies or whatever, and forces are just effective description, okay? If you don't want to go into too much detail, you can just replace a lot of analysis of how energies are flowing into, okay, effectively it's like if there was a force there, okay?
So,
yeah.
So that things like forces, perhaps momenta, energies, it seems that they are a little bit like auxiliary objects in a sense that when we measure the force, because we have like Newtonometers, but they were more invented in order to be capable of measuring forces that were before introduced by a theory, as I understand. So well, as far as we were
force meters is just a spring.
Yeah, exactly. So
it's just, you just convert, you just motion of spring convert into newtons, right? It can work without concept of force at all.
What I mean is that we have physical objects that we call physical quantities and are indeed observables in the sense that we first were observing them and then we were like speeds, positions, times, we'd say.
You're almost done.
Yeah, and they are somehow physical in the sense that we are observing them and this is what we want to predict from the theories, and forces were not observed. Well, okay, well, we were experiencing forces maybe somehow.
Well, it was force. Look, this is a whole story about forces, which is, I think, kind of interesting. The force because we push stuff, but then the forces on distance, that was with force fields. So there is how to interpret that. And this
we have the same experience, like there were a force with the inertial forces. Yeah, but
that's also very, very weird. Yeah. So
the human experience is the same.
But people immediately were suspicious about force because that from school, from high school. Okay, how do you define force? Well, it's acceleration times mass. Okay, so what is acceleration? Well, it's force divided by mass. What is mass? It's force divided by acceleration. There's no straight answer what force is. And if you don't have straight answer what force is, it can be anything, right? And this is how Newton mechanics works. There is some force. There are basically no limits what it can be. Just cannot depend on higher derivatives than second than first of the position, and that's it. But Hamilton formulation explains forces in different ways, more fundamental ways. And this is what people wanted. And this is what their critique, and this is what driven the whole proliferation of reformulations of classical mechanics, which still coexists together to this day. Okay. And this brings us to we are at the end. The pieces are in place. Okay. So one more thing one more critique that's kind of important, especially for non-classical theories. It's also part of critique of explanations, and it's a part of critique of experimental observations. It's like, you remember, the non-classical theories had to use measuring devices in their interpretations. Like, this is like a very important thing. And, you treat them as primitive notions, right? You assume you don't have to explain how they work, but you could kind of ask, okay, but how do they work? Can my theory like tell me something about those devices I am using? Right? Can I kind of have a feeling what they are? Because I just have to believe that they're working as I think they're working, that sometimes I will be just wrong, right? I have to have some criteria to tell if this is a good measuring, is it a good clock? Does it have all the properties that are required from the clock? And stuff like that, right? So this is like a critique only applies to non-classical theories. And it's like, this is essentially a problem of observer. An observer is like a model of a user inside the theory, okay? You want to ask, can I do that? Is it possible to do? Because it would be very helpful. And there are, with theory of relativity, so I would say the first one that, proudly used measuring device as a part of interpretation, this was one of the first things people did. Can we model inside the theory the clocks? Because clocks, Einstein wanted a couple of things from those clocks. For example, they can be synchronized, because theory of relativity means that there is no absolute reference frame, no absolute motion, no absolute time. So for clocks to actually be able to measure time, because a whole collection of clocks attached to your measuring sticks, essentially, right? This is how this works. So they have to, count the same time. So they have to be synchronized. And people were like, okay, hold on. Is it possible to do that actually? And to answer this, they made a model of clocks. It was basically bouncing mirrors, and mirrors that bounce light pulses in between them. And it worked. People agreed this is a good model of clock. It had all the properties, and you could like use it as a justification for the rules of interpretation. Okay, you cannot derive those rules because it's not one axiomatized system, but you can build a model that justifies your rules in interpretation. That Einstein's demands were okay. It's possible to satisfy them. But there was more, because the clocks, the synchronization method they used to model it, it's used in GPS satellites to this day. So it's also practical, not only just curiosity, not only critique, obsession or stuff like that. It's good practice to do. And this brings us to the end, because, okay, so let me summarize our journey here. So what I try to say to you is that you have your theories. They have this certain structure, like the math, but it's not only math. There is also this fuzzy bit of interpretation. that uses sometimes measuring devices if you have non-classical theories, like quantum mechanics uses measuring devices. But those theories are ever changing, right? They're evolving. And they're evolving because we are asking questions about them. And the best kind of questions we can ask is how they explain things. Okay. We can also ask about experiments, but that's boring. And like when we ask enough questions and we identify problems, because if you ask enough difficult questions, something might break. Okay, this is the impulse for doing refinements in your theory. And it happens many times throughout history of physics. Okay, it can even lead to like a forking of the theory. I mean, that you have different reformulations. Okay, so completely different formalism, like Hamilton formulation, Newton's formulation, whatever else. Quantum mechanics is not exempt from that. You can also do this for quantum mechanics, right? And like the last point I made about asking about measuring devices, this will be actually our vector of attack on standard formalism or quantum mechanics. Because like I said in the beginning, the plan is to first analyze the formalism of standard quantum mechanics. Now we have some tools how to analyze theories and to point out some shortcomings. Those shortcomings will be our critique of measuring devices, models of measuring devices. And this will be our catalyst for, okay, maybe we can do better. Or at least, fix some of those problems we identified. This will lead us to, the rest of the lecture where we'll be trying to derive what the deuce is a better word, the formalism, the rules of interpretation and stuff like that from some basic, essentially phenomenology of experiments with quantum systems. And I hope I managed to convince you that it's not heresy. It's okay. Not yet. I mean,
I think that vice versa.
yeah. But this is a practice. I would say this is the best type of doing physics, at least for me. I like it the best. When you open the boxes and try, whinging about what's going on there. And once you whinge enough, you want to do something about it. I mean, okay, let's try do it better. And if it succeeds, you're happy. If it fails, you learn something about your theory, about fundamentals of your theory, or maybe even foundations of your theory. Hence the title. So that was my spiel. Okay. I hope it wasn't super boring, and maybe even there was some fun here. I had fun. And actually, this is the only thing I care about at the moment. I was a little bit nervous about it. Okay, I was very much nervous. But thanks to Mariusz, it was much better than I thought it would be. And again, all this rambling, I will try to finish my paper, my essay, let's say, make it more pretty, and it will be on the website if you want to read it again, or maybe not, maybe don't read it again. But again, for me, it was very illuminating. Once I realized that, you can, it's not like theory is something you just given you from the heavens, and it's just, don't fiddle with it, but actually that you can do stuff with it, and it's all okay. And that you have this, maths part, which is separated from the words part, when you have interpretation. It doesn't have to be interpretation for humans only. It was like very, very eye-opening to me. Okay, I think the most powerful thing was that I made it my goal to think about non-classical theories without talking about quantum mechanics, because for me, at least, quantum mechanics was the thing, the weird thing. Okay, it's special. It's different than the rest. Everything else is simple. No need to think about it. So I try to force myself. Maybe that's not the case. And It was really fun to discover that, well, I can just take relativity and see, well, it's just like quantum mechanics, just quantum mechanics is just more of that. I was like, oh, that's cool. And then think about classical mechanics again. There's a lot of stuff there. I mean, people were talking about it for centuries. There's a lot of very smart people who written a lot of very, very super extra intelligent stuff about measurements in classical theories. Poincaré wrote a lot of stuff about this. It's like we are not so smart that we are talking about these fundamentals with quantum mechanics. People already talked about it with classical mechanics. They were smarter than us, I think, because we are forced to do it, and they were just, you know, they felt the need. They had their obsessions. So yeah, so the next time we will talk about quantum mechanics. Okay.